Welcome to this presentation about jumpstarter. Jumpstarter is a project from the Edge team at Emerging Technologies Red Hat. You can find more details in our website jumpstarter.dev. I will start with a disclaimer. Jumpstarter is a project from ET currently in MVP stage. It's not a product and could be productized or not based on results. You can also find other ET projects at next.redhat.com. Let's have a look at the gap that most customers experience in the Edge space. We are really used to the data center world, where servers have out-of-band management and plenty of other options exist, like, for example, VMs. But in the Edge world, devices have specialized hardware that it's very hard or very difficult to emulate. And most of the time, that hardware is surrounded by lots of peripherals and devices. This lack of out-of-band management makes Edge devices difficult to test. Integration testing becomes a challenge, mostly because we don't have hardware emulation for all the surrounding elements. In a traditional server landscape, we will just create a VM for testing, but here we can't. Or when we can, it's far from complete. This leaves Edge devices outside of the CI/CD cycle in the manual testing. In addition, scaling becomes much more difficult as customers adopt more Edge hardware variants. We have seen customers with tens of variants. This is how DALI imagined a testing lab, where Edge devices are flashed with the latest firmware by a human operator, one by one for every firmware version for every device. It clearly does not scale. Let's not talk about testing pull requests. Let's see how we tackle those problems with Jumpstarter and hardware in the loop. Jumpstarter encapsulates Edge devices, introducing specialized out-of-band management and bringing those devices back into CI/CD pipelines. The continuous testing of hardware with software is what we call hardware in the loop of testing in CI. With Jumpstarter, we allow existing software to incorporate Edge devices into their pipelines. We want to pave the way for our customers to move from this into this. This is what Jumpstarter enables. In this diagram, when the pipelines have built our software and then an image for our device, Jumpstarter takes that result at the testing stage and flashes the device, controlling the power up, interaction, making sure that the desired testing is performed. We have tested in GitLab and Tekton so far. Other platforms like GitHub or Jenkins should not be different. Some notes about Tekton. Tekton functionality has been validated in single-node OpenShift. Supporting tests over multiple nodes would require improvements, like the implementation of a dynamic resource allocation plugin, the evolution of the device plugin in Kubernetes. How does it work? Jumpstarter can perform all the operations from command line, and I will show that later on a demonstration. But the most powerful feature is the script control. Jumpstarter supports a script language that controls the device under test. It starts by selecting one device based on the selector tags. It will wait until one is available for use. Then, the steps define actions to be performed on the device under test and the storage, like power on, power off, flashing, and cell interactions. More advanced tasks can be performed with Ansible when the basic startup is done. But that's just one option. You can address the device from any available shell command on the test host. Finally, there is a cleanup section where cleanup actions are defined. Those cleanup actions are performed at the end of testing or when something goes wrong. This is how a script run looks like. We'll see more of this on the demo. Let's talk about test harnesses. A test harness is a piece of equipment which connects the Jumpstarter software to the device under test. Jumpstarter is designed with a driver architecture. This allows Jumpstarter to work with other types of test harnesses. For example, customers who already had custom-built harnesses or other emerging test harnesses for Edge devices. We provide a driver for the jumpstarter board that I will talk about in a second. but the design is open to allow additional test harnesses providing similar functionalities. To make jumpstarter possible, we had to work on a test harness, since we didn't find any suitable one for its devices. This is how the jumpstarter-board project was born, an open hardware project that provides test harness capabilities to a wide range of edge hardware. This is just an initial version of the board, and we are collecting feedback to make it more useful. With this, we provide the ability to meter power consumption, control the storage, the power, a serial console, and digital I/O. It provides a variety of mounting holes to help mounting the device under test on top when possible. The jumpstarter board is designed in the mini ITX format. This enables mounting on standard server rack cases. Going back to integration with standard software pipelines, let's look at how GitLab integration can be performed. A GitLab runner is hosted on a server or a VM and has multiple jumpstarter boards attached via USB for the jumpstarter board driver, of course. And then the runner can simply use the jumpstarter command on the GitLab CI YAML. For Tekton, jumpstarter boards can be attached to OpenShift worker nodes. See the documentation on Jumpstarter plus Tekton to understand the current limitations and the work that still needs to be done to work beyond single node OpenShifts, but SNO is already possible. This is a diagram of what's happening inside a Jumpstarter board and the possibilities for expansion. In this example, we can see sensors and video injectors which are triggered by the Jumpstarter pins. Another possibility would be using multiple Jumpstarter boards to control multiple interacting devices at once. When sensor or video data is fed through the network, OpenShift can be used to inject the data stream into the device under test or to interact with the device. Okay, after many rolling eyes, I had to introduce this section. Since Red Hat is a software company, I guess I need to talk about open hardware in Red Hat. We don't manufacture hardware, but we're making it easy to use on-demand manufacturing in a way that anybody could order Jumpstarter boards to be made on demand. We have seen around 1 month lead time. We're also looking for partners who could be interested in selling already manufactured and tested Jumpstarter boards. And of course, we are also looking for companies who could be making similar products and want to see their products supported in Jumpstarter. But having at least one fully open source test harness enables lots of opportunities. Customers can access the hardware without depending on a vendor, but they can also pick a partner that offers additional benefits or support on the hardware, like tested hardware, whole packages of wires and accessories, and so on. We, as Red Hat, will be focused on the software, and in the meanwhile, our customers and partners will have the ability to customize their testing harnesses if they ever need to. The design is future-proof. Anybody can take it, enhance it, or make an updated version. And finally, and most importantly, open is in our core. So at this point, I guess it's demo time. Let's go. Okay, so let's look at the Jumpstarter command line. Jumpstarter is currently distributed as a single binary. It's a command line tool, so you can do most of the actions from the command line, but you can also run scripts, and we will show that later. First thing, you can list the drivers available in this build. So far, the Jumpstarter board, but as we explained, we want to support other test harnesses. We can list devices for the supported drivers, and as we see here, we have 3 Jumpstarter test harnesses. Each of them has a different device under test. Each of them has a name, a set of tags to let us address them, and a serial port for communication. We can look at the configuration of any of them. You can address them by serial number or device name. And as you see, this is the current configuration. For this one, it has a name, the tags, storage filter that allow us to only write to specific storage devices. You want to filter and make sure that we are never going to confuse multiple jumpstarter storages. We can use that. If we have an out-of-band console that is going to be available via a different USB console because it comes with the device, or because we need just a separate console, we can specify a filter for that. And Jumpstarter will take care of looking up for that console. And then we have power profiles. Power profiles explain to the low level firmware how to perform power on, power off, and a special profile that we call rescue to put devices into flashing mode. So, for example, if we do Jumpstarter power on, the first profile is going to be executed. We could do that with the Orinex. We can also request the attachment of the storage, and we can also request a console immediately. So if we do that, we'll see, let me scroll up, we will see the device being powered on, the storage being attached to the device, and then the boot up process. At some point the UEFI BIOS is going to detect the storage and boot. Yeah, this is our image. So let me exit this console. I will do Control B. Yeah, and there we are. And let me power off this device for now. As you can see, the Jumpstarter has several LEDs on display. One for indicates that a command has been received on the Jumpstarter. This one is for reception of data from the device under test console, transmission to the device, and then the power of the device under test. This other one indicates that Jumpstarter has power. A very important function is the ability to write to the attached storage. In this case, let me move the camera a little bit. We have a USB stick attached to the Jumpstarter, and we use that for storage. Anything USB 3 ideally is going to be working perfectly. So let's write that storage. We get an image that we have here from a GitLab build. Jumpstarter will connect the USB storage to the host and read the image to the device. As you can see, this happens pretty quickly because we are using USB 3. And yeah, we think that being fast in this operation is important, especially if your images are bigger. You really want to iterate quickly on testing. The quicker you test, the more you can test. So yeah, this is finished, and we could boot from that image at this point. We have other commands. We can make sure that the storage is attached. We can do that. To the device. We can also detach the storage. We can control power with the different power profiles. We can perform a reset on the device via the reset signal, and we can also toggle the control pins on the digital I/O. For example, set control or in NX00. Sorry, that's high impedance, but we can set it to low. We do that. Let me show the kernel output. We do that. We have set the A signal to low. A signal is connected to the flashing ping on this device. When we power on, this device will go into flashing mode, and it's identifying via the USB bus as being in flashing mode. We can power it off, and we can release that signal. But this will be equivalent to doing a power rescue. We can change the name of any of the devices, set name, with this command to make them easier to locate. That configuration is stored in the jumpstarter, so if I unplug it, we try to list the devices here. We see the device is gone, but if we plug it back, the name is still there. Let me put it back to the original name. Yeah, and those are the commands for manual control. The most important one is run script, which is the one we explained in the presentation. We run a script. We can do jumpstarter. Let me we can automate our testing. In this case, as we can see, and I'm keeping the kernel output so you can see what's going on. We are writing the image as the first step, and when the image is written, we will power on the device and wait for login. Once that we have login, we will update the kernel, install some kernel modules that we are trying to validate into this hardware, and then perform a series of tests. We're using this in production to verify kernel modules that we build. At this point, it's booting and waiting for the login. Our image has a pre-configured user and password, so we can just log in from the console. Yeah, here the login appears, and we just log in, update. So we get an update on the kernel package, and then we will install the kernel drivers. Let me stop this, and let me show you how the script looks like. yeah, so the script is looking for an ORIN device, then powering off, writing the image that's in the storage, then waiting for the login, as you saw, updating the kernel, then it will install some modules that we built, and then reboots. And after reboot, it's going to validate that the kernel modules have been properly installed, and we will continue in Ansible because we can run more complex tests that we need to run, and yeah, capture artifacts at the end. So yeah, let's now have a look at the internals of the jumpstarter, because there are some features that we are not exposing yet in the software. So jumpstarter list devices. You see here we have the port for each of them. So if we do screen, we get into the console for this device. We can perform a help command. We can get the version. So at this point, we are talking to the chip into the jumpstarter board. It's a hardware device. This is programmed in Rust. You can find the code here. Yeah, that one. You have the firmware. You have a bootloader and an application. We use a bootloader to be able to update the jumpstarter from the testing host. So things that you can do from this console are metering power. For example, you can do meter read, and that is going to give us a reading of the current power consumption. If we power off the device, let me do a monitor on to see the output of the console and send power off. We're going to power off the device. Meter read. Yeah, you see the power is. We can verify here that our device is not really powering down in the way that we expected. If we power off the device completely, then yeah, we have a clean reading. We can also do meter on and power on, and then we will get meter readings at each line of the console output. We are looking for other options to send those readings, for example, via a control command in the USB bus, so it will be completely independent of the serial console. And so we could gather statistics of power during any test. For example, getting the maximum, minimum, and the whole historical series of data. Let me power this off. From here, we can also control the attachment of the storage. For example, we could do storage off, and now the storage is connected, is completely disconnected, or we could do storage host, and we connect it to the host. Yeah, you can see the kernel has found the device, storage off, the device is disconnected. We can also get the config. We can set control pins. For example, the reset signal, we can set it to low, and now if we power on, nothing is going to happen. So we can lift that signal and we can put it down again. And we can also set configuration parameters. That's what the jumpstarter binary is doing. So let's disconnect from here and let me share the details on the hardware. We have ideas to improve this because this is like a most simple version that we could make in a very short time, but we have been gathering feedback and we want to use that to make another release. So if we go to the root page, you see the control connection on the jumpstarter. That connection is the connection right here. You can see it, yeah, that one. And that goes to the microcontroller. It's an STM32F411, I think. Yeah. And we use that microcontroller to control the device under test, meter the power, and control the storage attachment. This is the device under test control side. We receive from the microcontroller signals like the transmission, reception, the control pins, a reset signal. We also received the on-off that goes straight into a load switch. And the input can come from the power input for the device can come from a barrel jack connector or the USB-C connector. You are using USB PD. The voltage that we support is up to 20 volts. Then we have an Allegro device that can meter up to 5 amps. And from that we get a current sense signal. We also have a voltage sense signal via this voltage divider. And the mounting holes for the device. And this is the storage multiplexer. Here on the side is where we connect the storage that we move between the host and the device under test. We have a couple of load switches to control if the power comes from the device under test, in this case, or if the power comes from the testing host. Then we have a switch for the USB high-speed signal, and then a switch for the super speed USB signal. Let me open the PCB. Yeah. So on the PCB, this is our microcontroller. The power input section and power metering load switch. This is the USB connector that goes to the testing host and provides storage connectivity. This is where the storage device is connected. We want to move this connector inside instead of looking outside. We believe that it makes more sense to hide the storage device inside our server rack case. This is the USB connection pin for this is the USB connector for control, and down here we have the control signals that go to the device under test. We have the storage connection and the power output. You either choose barrel jack or USB PD. You see that here on the top we have a set of buttons. This button down here is used to put the chip into factory programming mode. You can program the chip via USB. You don't need any programmer. There is a debug header here for just in case it's ever needed, but we didn't need that so far. We tested it, but yeah, we didn't really need it. We also have a DFU programming mode button to force the jumpstarter to go into the bootloader that we program on top, and a reset button. Let me show you the details on DFU. By using the DFU protocol, we can do things like this. We can use we can provide updates to Jumpstarter via the firmware update daemon. It's still reporting a couple of issues that we had in the past. I need to figure out how to clean that up. But yeah, the idea is that we can distribute the firmware for Jumpstarter via in the LBFS project and firmware update. This is available on almost any Linux distribution. You can also use DFU util. Let me try that. Yeah, we look at that. Those are the 3 jump starters which identify themselves as DFU enabled. Let me remember the programming. So you want to change the firmware in one of them, for example, this one. Let me use an older binary. Yeah, the device will detach, but it's attaching with a new device number, and the util does not seem to track that, but we can program it now. And at the end, it will simply reattach. Yeah, we can see this is the previous version. The difference here is that, I mean, the advantage here is that we can just update Jumpstarter from the testing host without the need for manual operation. If anything went wrong, still we have the options to have an operator go and factory reset if we need to update our bootloader or force the bootloader manually. And Jumpstarter list devices. Yeah, it should tell us now that this one is on the 006. And I can put back. the latest version. Yeah, and there we go, the firmware for the jumpstarter test harness can be found here. You have the application running inside. This is the code for the shell and the different commands on the shell. You have the module to store configuration. Configuration survives the update of the device, unless there is a config format change. Yeah, you have the power meter, a filter for the power readings. And that's it. So if you made it to this point of the presentation, thank you very much for listening. I'm Miguel Angel Ajo from the Edge team at Emerging Technologies at Red Hat. Please reach out to me. This is my email address. I'm happy to collaborate, brainstorm, and look for possibilities.